Okay, we've had a look at the introduction to integration and what integration is all about, the anti-differentiation process. I just now want to start off this little section on definite integrals and then leading into area. I want to start off by talking about the difference between an indefinite and a definite integral. So they're on the screen. An indefinite, you just pick the difference. You should be able to see the difference straight up. Now the definite integral has these what we call terminal values. Okay, then and a definite integral can be evaluated. We come up with a numerical answer. An indefinite integral can't be. There's no terminal value, and what we end up doing is just finding an integral expression, and we put a plus c on the end, and we're done. But these are the difference here. These terminal values. When we start talking about those, an upper terminal value and a lower terminal value. And we'll talk about what that is, but normally we're looking at the higher number on top and the lower number underneath, and this leads us into area as discussed. Okay, so an indefinite integral, if we're integrating 2x, then simply we're taking 2x, we're upping the power by 1, we're dividing by that new power, and we're plussing c, so we end up with just x squared plus c. When we are finding a definite integral, as in we've got our terminal values, in this case 4, 0, this is how we proceed. What we do is we open up some square brackets, and inside that square bracket we integrate the function 2x. So it's exactly the same as we just did here, except we do not write the plus c, we just write the x squared. Then conventionally how we set it up is we put our terminal values top and bottom of the square bracket, and our next step is to substitute those terminal values into my integrated expression, into my integral. So 4 goes in here, so I'm now going to take 4 squared and I'm going to subtract 0 squared. And so the value of my integration, my definite integral, is 16 minus 0, or just 16. Okay, definite integral comes up with a numerical answer. Okay, let's take a look now at how this definite integral relates to area. And I've mentioned before that that's where integration has its greatest application is in calculations of area. Okay, so what this does? Okay, this definite integral here, 2x between 4 and 0. What it does is it finds the area bound by my function y equals 2x, x equals 4, and x equals 0. So if I drop down, let's say x equals 4 is just here, x equals 4 is 0, obviously x equals 0 is there. What this does is it finds that area there. So that is the value, that area is equal to the integral of this, whatever that curve there is. In this case it's the straight line 2x, and so that's one boundary. My other two boundaries are the x values 4 and 0. So x equals 4 and x equals 0. Okay, now I've already found that out to be, I've already evaluated this to be 16. Let's just check, because it's a triangle and we know how to find the area of triangles. If we just do area is equal to a half base height, then we get a half. Our base is 4, and what's our height? Our height, this distance here, is put 4 into this function here to get the y value, and that will give us our height. So 2 times 4 is 8, so a half by 4 by 8, which equals a half by 2, sorry, half by 4 is 2 times 8 is 16, so it's 16 units squared, and you can see that I'm matching up here. So definite integrals lead into our work on areas. So if we're looking for the area, we need to bring it in in this case we wouldn't need to integrate because it's a straight line and we can use our knowledge of triangles. If we have a curved boundary line between two values a and b, then that area there, if this is the function y equals fx, then that area in there is equal to the integral between b and a of my function of x with respect to x. So it's bound by that x there. It has to be in terms of x for the x-axis being a boundary. So if we have a look at, if we were looking at, as we sometimes do, a y-axis boundary, then this would have to be in terms of y. So if you think about a boundary, what is this area here bound by? It's bound by the curve, function of x. It's bound by x equals b, that straight line there, x equals b, that straight line there, x equals a, so b and a. So 1, 2, 3 boundaries, 1, 2, 3, but also the x-axis, and that's where our dx comes in. Let's make sure we are integrating with respect to x. So that's how area fits in. Let's have a look at an example, another example of a definite integral and another area example, and then we'll be ready to get on with the next exercise, 23D. Okay, looking at some examples now. The first one here is from 3 to 2 of x squared. So what we do is as soon as we're ready to integrate, we open up the square brackets. X cubed over 3 is my integrated expression, and I'm going evaluating between 3 and 2. So my next move is to substitute 3 in here, so I get 3 cubed, which is 27 over 3, and I subtract 2 cubed, which is 8 over 3, so my result is 19 over 3. 19 over 3. Now what I want to do is have a look at how it changes when we flip the 2 and the 3 around. So same expression here. So I've still got x cubed over 3, but now I'm going between 2 and 3. So at 2 it's 8 thirds, and at 3 it's 27 thirds, and so I end up with minus 19 over 3. So what you need to appreciate there is that when our terminal values switch, we will get the negative result. So keep that in mind, that's an important one. Down here, just one more example. Now this is a sum of. What we can do is just work out what each integral is independently. So add 1 to the power, x to the 3 over 2, divide by 3 over 2. Do the same here, we get x to the, add 1 to 3 over 2, you get 5 over 2, divide by 5 over 2. Alright, we'll tidy that up, but that's going to go between 1 and 0. Let's just tidy up these fractions, make it easier for us to work them. I'd like us to get into the habit here. This is a fraction 3 over 2. So multiply top and bottom by 2 to get 2x to the 3 over 2 over 3 plus 2x to the 5 over 2 over 5. Right, that's between 1 and 0. Now we're going to sub 1 in here. 1 to anything is 1, so that's 2 thirds. Plus we've got to put 1 in here, 2 fifths. So that's substituting 1 in. Now we subtract, putting 0 in. It's going to be 0 plus 0, is it not? As soon as 0 goes in there, then it's all zeroed up. So our result is 2 thirds plus 3 fifths, which is 10, 16 over 15, I think is our result there. Okay, so final example here is to find the area enclosed by the graph of y equals, and it's in factored form, which makes it easy for us. So it's a cubic, and I've drawn it there, and it's in factored form, so I can see the x-intercepts are 0, 2, and 3. That's nice and easy. And the x, so enclosed by the graph and the x-axis. So this is the x-axis here. So enclosed by the graph and the x-axis are these zones here. So what is the combined area there of those two? Now, first thing for us to understand is that an area above the x-axis. So if I was to evaluate here between 3 and 2, if I was to evaluate this expression here, sorry, the integral of that expression between 3 and 2, I would get a positive result. But between 2 and 0, I'd get a negative result. Anything under the x-axis comes out to be negative. So what we can do to adjust that is we can perhaps flip the terminal values around to get a positive result that way. But firstly, we need to acknowledge, right, so we got an area to find, so let's get down to work. My area is equal to, and let's go between 3 and 2. Right, I'm going to go between 3 and 2 of, right, this function x minus 3 dx. Right, that's going to give me that zone there. Right, then I'm going to add between 2 and 0, but if I put 2, 0 here, it'll be negative. So why don't we go with 0, 2 of the same function x, 2 minus x, I'll just change the order around, 2 minus x dx. Now that is that area there, but in a positive version because I've gone 0 and 2. Okay, that's just to balance that effect out, or neutralize the effect of it being under the x-axis. So I'm going to just pause for a minute here and do some algebra so that you don't have to work through it. Or as I do this pause, perhaps you can work through the algebra. And what I'm going to do here is expand this expression out. So I've got something I can integrate, and then we're going to integrate it and evaluate it between those values, and we should therefore at the end of that process end up with the area, the combined area between the curve and the x-axis. Okay, I've done a couple of lines of work, and what I've done is I've just expanded. Firstly, I've multiplied the x by the 2 minus x to get 2x minus x squared, and then I'm going to multiply that combination by the x minus 3. It's always the best way when you've got 3 or more factors to multiply out. Then just just work from the front, multiply the first two out, then bring in the next factor, and just keep going until you're done. So I've multiplied those two to get this. Now I multiply 2x minus x squared by x minus 3, and I've got this. I'm going to just simplify this out. So I've got minus x cubed if I work in descending powers of x. 2x squared plus 3x squared is 5x squared minus 6x. I think that's my expression. That's now what I'm looking to integrate and then evaluate between 3 and 2. So I can just, over here, it's the same expression down here between 0 and 2 of minus x cubed plus 5x squared minus 6x with respect to x. Okay, so we're ready to integrate. Bring in the square brackets. I'm now going to add 1 to the power, divide by it. Add 1 to the power, divide by it. It's a 3. Add 1 to the power, divide by it. And I'm going between 3 and 2 there. Same over here. I'm going to have exactly the same expression. This is 5x cubed over 3, and 6x squared over 2 is 3x squared. And that's between 0 and 2. So substituting those values in now, 3 goes in for x, so I get 3 to the power 4, which is minus 81. Now that's minus x to the power 4, so it is going to be minus 3 to the power 4. So it's minus 81 over 4. 3 goes in here, 3 cubes is 27, 5's 135, so it's going to be 1 plus 135 over 3. And then we've got, this is 3x squared, 3 squared is 9, so that's 9 3's are 27. So 27 goes in there. Now that's just for 3 going in. I need to subtract 2 going in. 2 going in is going to be minus 16 over 4. 2 going in here is 5 times 8 is 40 over 3. So there's a lot of calculation to be done here. 3x squared with x being 2, is 2 squared is 4 is minus 12. That's just this section here. I'm now going to do the same over here and put in 0 and 0 and 2. I'll pause. Okay, there's a fair bit of arithmetic to be done here, but it comes out to be 37 over 12 units squared, and I'm sure you could access the calculator through most of this. But it's the process that I want you to understand and also get some more practice with as we go into exercise 23D. So I'll see you in class.